Welcome to this explainer. Over the next few minutes, we're taking a step-by-step journey into a technological shift so massive, it's literally redefining how we build the world around us. We are moving entirely beyond the theoretical boundaries of classical physics and stepping directly into applied quantum mechanics. Now, this isn't some distant science fiction. What we're looking at today is a validated blueprint of the state-of-the-art from 2024 to 2026. I really want you to focus closely on the visual data we've selected for you today. We're going to take this nice and slow so you can really get a good look at these incredible documents as we map out exactly how fundamental physics is being converted into applied technology. Okay, let's dive into this. Notice that rigid, highly structured crystal lattice. That right there is classical order. That is the physics our entire current civilization is built on. But as you follow the progression through the phase transition, you see it shifting into continuous wave functions. We are looking at the fundamental redesign of material civilization, moving from static, fixed structures to highly dynamic quantum states. It's a complex, honestly beautiful transition, and it establishes the overarching blueprint for everything we are about to explore. Take a second to really let that visual sink in. So here is our mental roadmap for today's architectural tour. Section 1, the end of the classical limit. 2. Horizon 1, topological materials. 3. Horizon 2, algorithmic atomic design. 4. Horizon 3, quantum biomimetics. And finally, Section 5, the commercial quantum ecosystem. Starting with Section 1, the end of the classical limit, or basically bypassing the silicon wall. Our first stop is understanding why this shift absolutely has to happen right now. The reality: silicon-based innovation and chemical trial and error have just hit a wall. Quantum mechanics is no longer just a theory for physicists to debate in a classroom. It is now a necessary engineering tool to design matter, atom by atom. Take a really good look at this graph. Trace that thick, dark line representing classical physics. Notice exactly where it just flatlines. It literally cannot scale further in capacity. But right there at that bottleneck, what we call the quantum singularity line, you see our three technological horizons accelerating dramatically upwards. Perfect simulation, ultra-fast electronics, absolute biological efficiency. The future, well, it isn't just a refinement of that dark line. It is a massive leap onto those colored curves. And this brilliantly illustrates exactly why that classical line is flatlining. Look at the physical limits of scaling down silicon. All those arrows pointing away from the glowing red center? That represents massive energy loss and heat generation. It's completely exhausted. Now compare that to the quantum paradigm. Those loops and tracks are protected electronic states. They act like one-way highways for electrons, which means electrical resistance and energy loss drop to virtually zero. Of course, to build these one-way electron highways, we need a completely new infrastructure. Let your eyes move up through this beautifully detailed 3D schematic. We've selected this visual so you can clearly see the complete quantum materials technology stack. Down at the bottom, Layer 1, the physical foundation of topological materials. In the middle, Layer 2, the logical accelerator of quantum computing design. And at the top, Layer 3, the application layer of quantum biomimetics. We're going to explore every single floor of this architecture, starting right from the ground up. Which brings us to Section 2, Horizon 1, topological materials, the physical layer. This is the foundational hardware platform. Before we can even think about running advanced quantum algorithms, we need physical materials that actually harbor those protected electronic states to build unbreakable hardware. Now we are about to look at some slightly complex math, so let's preemptively simplify things. You just need to know two key terms. First, a Fourier pattern. This is created by taking two flat atomic grids and twisting them at a very specific angle to change how electrons flow. Second, a topological insulator. That's a material that acts as a perfect conductor on its surface, but a complete insulator on the inside, keeping those electron pathways perfectly protected. Now, what's really interesting about this slide is how we actually create those patterns. You've got perfectly aligned atomic grids in the first frame, but see what happens when we use twistronics? By twisting those grids by a critical angle of exactly 1.4 degrees, we create a Fourier pattern. That tiny, incredibly precise twist fundamentally alters the physical properties of the material, creating isolated flat bands. The math calculates this shift, but the core takeaway? We are literally programming physical topology just by twisting atomic layers. It's amazing. And, it's not just about twisting 2D sheets either. Here we see the structure of magnetic topological insulators, specifically from the Zintel family. Check out that europium ion, a highly reactive rare earth metal placed right there in the center of the crystal lattice. By combining magnetism with this non-trivial topology, engineers are synthesizing these incredibly robust materials with perfect conductivity in the lab right now. The hardware foundation is very real, and it's solidifying. Moving right along to Section 3, Horizon 2, Algorithmic Atomic Design. Welcome to the logical layer. Let's head up to the next floor of our architectural tour. This is where we use the massive computational power of quantum mechanics to actually simulate reality itself. What you are looking at here is the logical accelerator. And a truly crucial thing to note is that we aren't just sitting around waiting for perfect future computers to pull this off. Current NISQ hardware, which stands for Noisy Intermediate Scale Quantum Computing, is already capable of breaking through the computational chemistry bottlenecks that completely choke our best classical supercomputers. So how exactly do they do it? Through an accelerated discovery pipeline. Let's break this down step by step so it's super clear. First, classical generation uses machine learning to suggest thousands of possible chemical candidates. Second, quantum execution calculates the ground and excited states of those candidates. Third, classical validation uses supercomputers to verify the top results. And finally, physical synthesis means actually taking those findings and creating the predicted material in a lab. Let's move to the next slide and see how this builds into a continuous ecosystem. Here is that full pipeline we just defined, mapped out beautifully as a visual loop. Classical and quantum systems aren't competing here. They are working together in this incredibly precise circle, generating, executing, validating, and synthesizing. This closed loop drastically accelerates how fast we can discover entirely new materials. Up next is Section 4, Horizon 3, Quantum Biomimetics. The application layer. We've made it to the top of the stack. Honestly, what's truly humbling about this specific horizon is that human engineers are essentially just copying biology. Nature has been successfully utilizing advanced quantum engineering for billions of years. I want you to take your time with this visual because the concept is mind-blowing. Notice that massive mountain representing an energy barrier? In classical chemistry, to get a reaction to happen, you have to push a huge amount of energy up and over that massive peak. But look at that blue arrow piercing straight through the base of the mountain. That is quantum mechanical tunneling. Biological enzymes naturally use this exact quantum shortcut to bypass massive energy barriers. Nature's been doing this forever. It's how processes like photosynthesis actually work. By engineering systems that mimic this, we're unlocking zero-carbon catalysis and unprecedented levels of efficiency. And biomimetics isn't just about energy shortcuts. It's about sensing the world around us. Here we see radical pair magnetoreception. Again, this is not theoretical. We are actively engineering living cells like the maglev flavoprotein perfectly mapped out here to act as highly sensitive, optically detectable magnetic sensors that operate perfectly at room temperature. Just imagine medical diagnostics in the near future that are actually made of engineered living cells. That is exactly what this unlocks. We are literally turning biology into quantum hardware. Finally, let's hit Section 5, the commercial quantum ecosystem, from lab to market. Now, as fascinating as the raw science is, true innovation always requires capital and infrastructure. Let's transition to our final reality check to see exactly how this technology stack has successfully moved out of the lab and into the market. So, the crucial point is right here on this slide. We've selected this matrix to synthesize the entire ecosystem for you. Topological materials, they're already in Series A funding stages. Quantum compute design is actively providing cloud access to researchers globally. Quantum biomimetics is driving green catalysis startup commercialization. Every single horizon we've explored today is firmly anchored in real, validated systems and primary commercial applications. The proof, as they say, is in the capital. And here is the actual map of that commercial ecosystem. You can see the specific players driving this forward. Over in Horizon 1, notice Topologic Inc., with millions in Series A funding specifically for topological RAM. Right in the center, you see major compute platforms like IBM Quantum and Quantinuum, offering tangible, real-world cloud access. And then on the biomimetics side, startups like QT Sense and Basecamp Research are pushing into advanced diagnostics. Real money is moving, and the entire ecosystem is connecting. Which leaves us with a necessary, maybe even slightly uncomfortable, consideration. If the science is validated, the materials are synthesizing, and the commercial ecosystem is actively funded, we really have to look at our own foundations. Because as we've seen throughout this explainer, the classical limits are incredibly rigid. But the quantum horizons? They are accelerating endlessly upwards. Are we ready for that leap? As we wrap up this analysis of the technology dossier, let's just linger on this amazing blueprint for a second. Trace those intersecting lines of the atomic grids in the deployed code. The fusion of quantum mechanics and material science is no longer waiting on some distant theoretical breakthrough. The formulas are verified. The ecosystem is actively scaling. The blueprint is fully ready for execution. The only real question left is, how are you going to adapt when the rules of classical reality simply no longer apply? Thanks for joining me on this deep dive.